In the previous video, we saw how we can combine the equation for a line and the equation for a circle to find the points of intersection between the two. In this video, we're going to do the exact same thing, but we're going to approach it slightly differently. In the last video, we were actually quite lucky. Our equation for a circle centered about an arbitrary point isn't too complicated. It's only slightly more complicated than the equation for a circle centered at the origin. However, with other geometric forms, the more generic equations which allow for that geometric form to be transformed in various ways, they're often much more complicated than the most basic form that puts all these restrictions on the shape, for example, forcing that shape to be centered at the origin. Now, in these cases, the best approach is often to try and use that basic form of the equation, not the more complicated generic form, because if we can use the simpler equation, our mathematics is going to be a lot easier, it's going to be easier for us to solve. Of course, that basic form of the equation is requiring that our shape meet all of those restrictions. For example, with our circle, it requires that our circle is centered at the origin. Now, obviously, if we have a line that we're trying to intersect with some circle that isn't centered at the origin, that's floating in space, we're going to get different points of intersection than if we intersected it with a circle positioned elsewhere. We can see this quite clearly if I drew up some Cartesian axes. And I said, here is a circle floating in space, centered at the point AB, and it has a set radius. And let's say we have the exact same circle, but instead it's centered at the origin, so we can use our more basic equation. So it has the exact same radius, but it's centered at the origin. If I was going to have a line that intersects this circle somehow, and let's say it intersects the right and the top of this circle, something like so. You have to bear with my rather wobbly line there, but let's say we had a line that's intersecting that circle. We can see if we intersected this line with our other circle, we would be getting different points of intersection. We can see in our 2D space that these 2 points, there is no way that they are the same as these 2 points. They do not correspond. So you can see that we can't just take our line and intersect it with this more basic circle equation. We're going to get the wrong results. So to resolve this, what we need to do is we need to transform our entire problem such that we can use this basic circle. Well, how are we going to do that? That means we need to transform the problem so the relationship between our line and this circle becomes the same relationship between that line and our basic circle. And that means we need to make those two circles match. Now, we've already seen how we can make our generic circle match our basic circle in an earlier video. We're going to translate by minus a in x and minus b in y. If we translate by that, we're going to move our circle such that it is centered at the origin. So if we center our circle at the origin, it's going to match our generic circle. The circles are going to be identical to each other, and that means we could use this circle equation to represent our generic circle. However, we can't just translate the circle, we need to translate the entire problem. And that means we need to translate the line by the same amount. So if we were translating our circle by minus a in x and minus b in y, then we need to translate our line by the same amount. If we did that, the points of intersection of this newly transformed line would be the right and top of this generic, or rather basic circle centered at the origin if they were the right and top of our generic circle centered elsewhere. So by transforming the problem, we're now able to intersect this line by our basic circle equation, and that's going to give us the correct 2 points with regards to our circle. However, we can't just take these points, because notice, these are the points we were trying to find. We have just found these 2 points, which indeed the relationship between the line and the circle is correct, but they're still not the same. They're still transformed down where we moved our problem. So once we've found these points, we need to transform them back to the original location of the problem. We need to add a to their x coordinates and b to their y coordinates to translate them back to the original problem, and thus giving us the correct results. So in general terms, what we've just done is the following, and this is an incredibly important workflow. What we've done is we've taken a complicated problem, And we've transformed that problem such that it becomes a simpler problem. We've then calculated the results of that simpler problem. And finally, we've transformed the results back so that they're appropriate for our complex problem. Now, I really just cannot stress how important that generic workflow is for so many problems that you might encounter. I'm not just talking about intersecting shapes by using equations. There are a whole wealth of problems that are easier to solve when certain restrictions are put in place. So if you can transform your problem to meet those restrictions, solving the problem becomes a lot easier. Then once you have the solution, you can transform it back to get the true answers for the original problem. So one last time, because this is such an important workflow, you take a complex problem, you transform it so that it becomes a simpler problem, you find the results of that simpler problem, and you transform them back so that they're appropriate for the complex problem. So now let's take a look at that workflow in practice for intersecting our line and our circle, and we'll see how it will make life a lot easier for us. So I'm going to bring up a new whiteboard. There we go. And we know starting out that we have a line equation, and that is y is equal to mx plus c. And we know that we have our circle that we're trying to intersect it with, and that's x minus a squared plus y minus b squared is equal to r squared. But we're not trying to use our generic equation. We actually want to use our basic circle equation, which is x squared plus y squared is equal to r squared, because obviously this is a lot simpler. This equation is going to be easier to solve because we have fewer items involved, we have fewer numbers, fewer calculations. It's going to be a lot easier to solve. And we just saw on the whiteboard, for us to use this equation, we must transform our generic circle to match this equation. And by transforming it by minus a in x and minus b in y, we do indeed achieve matching this equation. And we saw we can't just transform the circle, we need to transform the entire problem, and that means we need to translate our line as well. So we need to translate our line y equals mx plus c by minus a in x and minus b in y. Now, to represent the fact that this is our transformed line, that is to say, to represent that it's, as I grab this, to represent it's this line as opposed to being the original line, I'm going to use a slightly different notation. I'm going to use the coordinates x dash, y dash to represent a point on the transformed line, whereas x, y represent our point in the original space of the problem. So that means our line equation for our transformed line is going to be y is equal to y dash is equal to mx dash plus c. And we've seen how we can transform a line. Original translation is going to be in y, and then we're going to perform a translation in x. So we've seen how we can transform a line in both y and x. In y, we need to transform by minus b, and we saw that to do that, we simply need to subtract b from our y coordinates, much like our c intercept values. So to translate our line by minus b is as if we just want to move our line down by b, which means y is equal to mx dash plus c minus b. Now, to translate our line in x, we've seen how to translate in x in the video that covered the equation of a straight line. If we recall, we saw that y is equal to m x minus tx plus c. And in this case, we know our translation in x needs to be minus a. We want to move by minus a in x. But you also recall we said we need to invert that translation due to the way that we want to sample the curve in order to actually create the effect of having translated the curve. We explained that back in the video on the equation of a straight line. Therefore, if tx is minus a, we need to add a to our x coordinates. We need to add a to x dash. So our transformed line, our fully transformed line, becomes y dash is equal to m x dash plus a, so our translation of minus a in x, plus c minus b, our translation of minus b in y. This is the transformed version of our line y is equal to mx plus c. So what will you notice about this? Well, firstly, because it's the transformed version of our line equation, we can now intersect it with our simple circle equation. We can intercept it with this guy. But you'll also notice, if we were to expand this, we've already said in that earlier video on the equation of a straight line that any translation in x becomes a translation in y. So we could expand this and we would get some translation in y that we know to be a single constant value, and that would allow us to simplify this equation further. And if we can simplify this equation further, it's going to make our life further down the line in solving this problem a lot easier. So in actual fact, we're not just going to use this equation to solve our problem. We're going to keep working. So I'm going to erase this box that drew attention to the equation because we're not quite done yet. And let's keep working with this equation. So if we expand it, we get y dash is equal to mx dash plus ma plus c minus b. Notice again, in the video over the equation of a straight line, we said any translation in x can become a translation in y. So all of this is just a big translation of our line in y, and it's a constant value. When we're solving our problem, we're going to know the gradient of the line, we'll know the intercept of the line, and we're going to know the center point of the circle that we're trying to intercept it with. That means all of these are numbers and they're constant for the problem, which means this becomes a single constant value. So if I was to rewrite this as y dash is equal to mx dash plus d, where d is equal to ma plus c minus b, if we calculate the value of d at the beginning of our problem, because it is a constant value, we now have a much simpler equation. We have an equation that's just as simple as our original line equation, but whereas in the previous video we substituted our line equation into this complex equation, in this video we can substitute it into this simple equation. It's going to make all of our expanding easier, which is going to be quicker. Then all of the solving of the problem is going to be easier, and there's going to be less operations. So it's just going to be, in general, a lot easier for us to solve. So let's substitute our line equation into this basic circle equation. Now, of course, we must remember that this circle equation effectively is our transformed circle, so it's using x dash plus y dash is equal to r. It's just a notation thing, but it is worth making sure that we are following the same convention. Since this is our transform problem, I'm using the coordinates x dash, y dash. And we can substitute our value for y into that equation, just like we did in the previous video. So that's going to give us x dash plus, and my apologies, it's x dash squared plus y dash squared. So x dash squared plus mx dash plus d all squared is equal to r squared, as I completely get the equation for a circle wrong. So it is x dash squared plus y dash squared is equal to r squared, not x plus y is equal to r. That is not an equation for a circle in any means. So x dash squared plus mx dash plus d all squared is equal to r squared. This is what we're going to expand and solve. Now, if I turn your attention back just for a second to our previous video, which I believe was on this layer, notice what we were trying to expand and solve in the previous video. We had this, x minus a all squared plus mx plus c minus b all squared is equal to r squared. So try and remember this just for a second. Now look at what we've got. Now we simply have x squared plus mx dash plus d all squared equals to r squared. This is much simpler already, therefore it's going to be easier to expand, easier to solve. In general, it's just a lot easier for us. Now I am running out of whiteboard space, so I'm going to rewrite this on a new whiteboard and then expand it so we can solve for the value of x dash. So that equation once again is x dash squared plus mx dash plus d all squared is equal to r squared. So let's expand that. So x dash squared stays the same. This is going to be plus mx dash plus d times mx dash plus d, putting in extra steps just so that we don't lose anyone here with the expansion. So x dash squared is going to add to mx dash times mx dash plus mx dash times d plus d times mx dash plus d times d, which is equal to r squared. So this is going to expand to x dash squared plus mx dash times mx dash is m squared x dash squared plus mx dash times d is going to be plus dmx dash plus d times mx is plus dmx dash. D times d is plus d squared is equal to r squared. Now, just as in the previous video, I'm going to collect these like terms and subtract r squared so that we make our equation equal to 0. So x dash squared plus m squared x dash squared plus 2 dmx dash plus d squared minus r squared is equal to 0. Now again, to help see where we're going with this, I'm going to group the coefficients of x dash squared, x dash, and our constant term as well, just as before. So we're going to get x dash squared 1 plus m squared plus x dash 2dm plus d squared minus r squared is equal to 0. So hopefully you can see, just as in the previous video, we can write this in the form of ax, in this case dash, but ax dash squared plus bx dash plus c is equal to 0. Again, using capital A, B, and C to distinguish from the lowercase a, b, and c that we do have as our constants in our earlier equations. So I'm using capitals here just to distinguish from them. And we know that a is equal to 1 plus m squared, so 1 plus m squared. B is equal to 2dm. C is equal to d squared minus r squared, and you'll recall that d is on our previous whiteboard. D is equal to ma plus c minus b. So d is equal to ma plus c minus b. Now take a look at these equations. These are going to be solved again using our quadratic formula of x dash is equal to minus b plus or minus the root of b squared minus 4ac all over 2a. But notice, a is equal to 1 plus m squared. That was the same as before. B is equal to 2dm. C is equal to d squared minus r squared. Yes, we do have to calculate d, but that's a very simple equation to calculate. Compare that to our previous video. And this is our current video, my apologies. Compare this to our previous video. Look at our equations here. Far more operations in order to calculate b and c. A number of multiplications, a number of subtractions here, loads of multiplications and additions and subtractions here. It's far more complicated, and we saw that when we were working out our examples. We had to go through loads of steps to calculate b and c. Whereas in this video, so I hide this guy, in this video our new version is far easier to calculate. So that's going to hopefully make our life a lot easier. Also, if we were programming this, I'd suggest that it would be more efficient because there are less operations involved. Now, of course, there's a lot more than just the number of operations when you are dealing with efficiency in computer programs. And I must admit, I haven't done any true testing to see if, as implemented in code, if this would be more efficient. But logic would suggest that it should be more efficient because there are far less operations involved. So given values for m, c, a, b, and the radius of our circle, we can now solve for the points of intersection as we did before. But we must remember, of course, that we are currently solving our quadratic formula for x dash. The formula is going to be that x dash is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. We're solving for x dash. That means once we have found if there are points of intersection and found the value or values of x dash, we must take them and we must translate them back to our original problem, because right now what we have found are the values of the x coordinates for our translated problem, our problem that's now centered about the origin. We must translate them back. And to save on calculations, I'm simply going to translate the x coordinates back and then use those in the original line to calculate our y coordinates. That's going to be fewer calculations, fewer operations than calculating the translated y coordinates and then having to move them back as well. So I'm simply going to take our values for x dash. Once we've found them, we're going to add a to them to translate them back to the original problem. Once we've got those, we can use our original line equation, that is the non-transformed line equation, to generate the corresponding y coordinates. So what I'd like to do, I'd like to use the same two examples that we saw in the previous video to test our new equations and make sure we get the same results. So bringing up from the previous video, our first test had a circle centered at the origin, and it had a radius of 1 and the line y equals x plus 1 intersecting it. And we saw that it intersects at -1, 0 and 0, 1. So with an m of 1, c of 1, a and b of 0 and 0, and an r of 1, I want to test our new equations and make sure that we get the same results. So I'm going to hide out that layer. I'm going to bring up a new layer to work on. So we saw that we had an m equal to 1, c was equal to 1, a and b were both equal to 0, and our radius is equal to 1. And our equations that we're using, we know that a is equal to 1 plus m squared, b was equal to 2dm, c is equal to d squared minus r squared, and d is equal to ma plus c minus b. So we can now calculate the value of d, then calculate the value of a, b, and c, then use our quadratic formula to find the values of x dash, transform those values back to the original problem, and finally find the values of y. So d is equal to m times a, so that's 1, times a is 0, plus c is 1, minus b, minus 0, so that's equal to 0 plus 1, minus 0, so d in this case is equal to 1. We can now find the values of a, b, and c, so a is equal to 1 plus m squared, is equal to 1 plus 1 squared, is equal to 2. b is equal to 2 times d times m, so that's equal to 2 times 1 times 1, so b is equal to 2. Notice how much quicker we are finding a, b, and c here. So already we can see the benefits of having transformed our problem to a simpler space. And c is equal to d squared minus r squared, so that's going to be equal to 1 squared minus our radius was 1 as well, 1 squared, so c is equal to 0. So to solve for x dash, we know that it's equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And we know to find if we are indeed intersecting, we calculate the value of b squared minus 4ac, and we see is it positive, is it equal to 0, or is it negative. So b squared minus 4ac is equal to 2 squared minus 4, a is 2, c is 0. That's equal to 4 minus 4 times 2 is 8 times 0 is 0. So that's equal to 4. We know as it's positive, we have two possible solutions. Therefore, our line does pass all the way through the circle, giving us 2 points of intersection. So we can now solve for x dash in both cases. It's equal to minus b. Well, b was 2, so minus 2, plus or minus the root of b squared minus 4ac was 4, so plus or minus root 4, all over 2 times a. a was 2, so 2 times 2. That means x dash is equal to minus 2 plus root 4 over 4, or it's equal to minus 2 minus root 4 over 4. Root 4, of course, being 2, so it's equal to minus 2 plus 2 over 4, or minus 2 minus 2 over 4. So equal to 0 over 4, or minus 4 over 4, which means it is equal to a value of 0, or it's equal to a value of minus 1. Now again, these are values for x dash. To find x, we need to take x dash and we need to add a to it. We need to transform it back. Now luckily in our case, it's going to be very simple because a in this particular example is equal to 0. So we're not actually adding anything to these values. So in our case, x is going to be equal to 0 plus 0 or minus 1 plus 0. So it's still equal to 0 or minus 1. However, if our center hadn't already been at the origin, so if a and b had not been 0, then there would of course be a translation involved for our x coordinates. So x is equal to 0 or minus 1. We put that into our line equation. Well, our line equation was y is equal to x plus 1. So y is equal to 0 plus 1 or minus 1 plus 1. Y is equal to 1 or 0. That means our points of intersection are 0, 1 and minus 1, 0. We can check that against our previous examples. So 0, 1, minus 1, 0. I believe it's on this slide. 0, 1, minus 1, 0. Our equation is working exactly the same as our previous equation. It's giving us the same results. And now I'd like to check that against our second example, which perhaps, or maybe that is this guy here. So our second example, yeah, that's correct. Our second example had the equation y equal minus x plus 4. We had a circle centered at 2, 4, and we had a radius of 2. If you recall, that gives us an m of minus 1, a c of 4, a of 2, b of 4, r of 2, and it resulted in the points of intersection being 0, 4, and 2, 2. So I would like to check that now. I'd like to use our new equations to calculate the result of this particular problem and see, do we get the same result? So I'm going to bring up a brand new layer to do that. And let's start out again by recalling that m was equal to minus 1, c was equal to 4, a was equal to 2, b was equal to 4, r was equal to 2. So the first thing we need to do, we need to calculate d. Well, we know that d is equal to ma plus c minus b, which is equal to minus 1 times 2 plus 4 minus 4. So d in this case is going to be equal to minus 2. We can see that the plus and minus 4 cancel each other. So d is equal to minus 2. We can then calculate our a, b, and c. A is equal to 1 plus m squared. That's going to be equal to 1 plus minus 1 squared. That's equal to 1 plus 1, which is 2. B is equal to 2dm. That's equal to 2 times minus 2 times minus 1. That's equal to 2 times minus 2 is minus 4 times minus 1 is positive 4. Finally, c is going to be equal to d squared minus r squared, which is equal to minus 2 squared minus 2 squared, So d is equal to minus 2 squared is 4, minus 2 squared is 4. So 4 minus 4 is 0. So c is equal to 0, b is equal to 4, a is equal to 2. We can now throw that into our quadratic formula. X dash is equal to minus b plus or minus the root of b squared minus 4ac all over 2a. First thing we want to do we have points of intersection? We need to calculate b squared minus 4ac. That's equal to, b is 4, so it's equal to 4 squared minus 4 times a is 2, c is 0. So it's equal to 16 minus 0, which is equal to 16. So yes, it's positive. We have 2 points of intersection, but we knew that because we are hoping to get 2 points of intersection. We're basing this off of the example we used in the previous video. So now we can calculate for the values of x dash. It's equal to minus b. Well, b, if we recall, is 4, so it's equal to minus 4 plus or minus the square root of b squared minus 4ac is the square root of 16 over 2a. We saw that a is equal to 2 there, so 2 times 2. So it's going to be equal to minus 4 plus or minus the root of 16 is 4 divided by 4. That means that x dash is equal to minus 4 plus 4 over 4, or it is equal to minus 4 minus 4 over 4. That means it's equal to 0 over 4 or negative 8 over 4, which means it's either equal to 0 or it's equal to minus 2. Now again, we must recall this is x dash, so to find x, we take x dash and we transform it back to the original problem by adding a. If we scroll all the way on up, a is equal to 2. That means we need to add 2 to both of our possible x coordinates. So x is equal to 0 plus 2, or it is equal to minus 2 plus 2. X is equal to 2, or it is equal to 0. We can now throw that into our original equation. Now our original equation is y equals minus x plus 4, so we can throw that into the equation. Y is equal to minus x plus 4, therefore y is equal to minus 2 plus 4, or it is equal to minus 0 plus 4. That means y is equal to 2, or it is equal to 4. That gives our points of intersection as 2 in x, 2 in y, or 0 in x, 4 in y. So again, that's 0, 4, 2, 2. Let's check our original problem. Not this guy, this guy. And we saw our points of intersection were 0 in x, 4 in y, 2 in x, 2 in y. So 0, 4, 2, 2, 0, 4, 2, 2. So indeed, we're getting the exact same answers, and that's fantastic. That's hopefully showing us that our new equations, though they're much simpler than our previous equations, they do solve the same problem, they do give us the same answers. So, okay, now it is time for you guys to try a question on your own. Now we're going to use the exact same question as we had in the previous video, but I'd like you not to cheat. Don't just take your answers from the previous video. I'd like you to use these new equations to solve the question. And the reason I'd like you to use the new equations is to get used to A, using these equations, and also just to make sure that you follow the entire workflow, that you're not missing any steps, because there is an important step that I'm thinking of. I'm not going to give it a name just yet, just so that I don't give too many hints, but there is an important step that if you're not paying close attention, you might miss, and it will give you the wrong results. So that question, if you recall from the previous video, that question, so question 1, tells us that we have a line, y is equal to minus x plus 11, and we have this intersecting the circle x minus 3 squared plus y minus 5 squared is equal to 9. Now last time we asked a question, does this line intersect the circle? We saw in the last video, yes it does. There are 2 points of intersection. So this time the question is simply using our new workflow, using our new equations, find those 2 points of intersection. So go ahead and attempt this. If you get stuck, or once you have your solution, unpause the video and I will work through the solution on the whiteboard. Okay, welcome back everyone. So the first thing we need to do, much as before, is determine the various pieces of information that we are working with in this question. So we know our gradient is equal to minus 1. We know our intercept is equal to 11. We know A is equal to 3 and B is equal to 5 from our equation. And as we saw previously, we know our radius is equal to the square root of 9, which is equal to 3. So we have all of our information. With that, we can calculate D. D is equal to MA plus C minus B. So it's going to be equal to minus 1 times 3 plus 11 minus 5. So it's equal to minus 3 plus 11 minus 5. Well, minus 3 plus 11 is 8. Minus 5 is going to give us 3. So D is equal to 3. Now that we have that, we can calculate A, B, and C. So A is equal to 1 plus m squared. So it's equal to 1 plus minus 1 squared, which we know is equal to 2. B is equal to 2dm, so it's going to be equal to 2 times 3. Our gradient is minus 1, if we recall. M is minus 1, so 2 times 3 times minus 1. Well, 2 times 3 is 6, times minus 1 is minus 6. So B is equal to minus 6. And C is equal to d squared minus r squared. So D is 3, so 3 squared minus r squared, well r is 3, so 3 squared minus 3 squared, well I think we know that that's going to be 0. So we've got our values of a, b and c. I'm going to rewrite these, so a is equal to 2, b is equal to negative 6, c is equal to 0, just check that's correct, so yep, a is equal to 2, b negative 6, c equal to 0. Now that we have these, we can plug them into our equation, so minus, as I attempted to write, minus x dash, that's not correct, x dash is equal to minus b, there we go, that's where that minus was stuck in my head from, plus or minus the root of b squared minus 4 ac all over 2a. Now we do need to check b squared minus 4ac, it should be a positive value, we know there are 2 points of intersection, we should be getting a positive value here, but let's check that, so b squared minus 4ac is equal to minus 6 squared minus 4 times 2 times 0. Well, we can already see that is indeed going to be positive because it's 36 minus 0, which equals 36. We can now solve for x dash, so x dash is equal to minus b, well b is minus 6, so that's minus minus 6, so positive 6, plus or minus the square root of 36 over 2 times a was 2, so that's over 4, so it's equal to 6 plus or minus 6 over 4. That means that x dash is equal to 6 plus 6 over 4, which is 12 over 4, or it is equal to 6 minus 6 over 4, which we know is 0 over 4. That means that x dash is equal to 3 or 0. Now here is the step that I mentioned a second ago as being a very important step, but if you're not paying close attention you might miss it. That's that we must translate x dash back to our original problem to give us x. So we know that x dash is equal to, my apologies, x is equal to x dash plus a. And a, we know, was 3. So x is equal to either 3 plus 3 or 0 plus 3. That gives us x is equal to 6 or 3. We can now put that into our line equation. We know that y is equal to minus x plus 11. So it's equal to either minus 6 plus 11 or minus 3 plus 11, which is equal to either 5 or 8. So our points of intersection are 6, 5 and 3, 8. Now, I know, personally, I remember this being the correct answer from previously, but let's double check that. So 6, 5, 3, 8. 6, 5, 3, 8. So indeed, using our new method, we've got the exact same answer, but it was, in my opinion, a lot easier using this new method to get that same answer. Now again, I imagine if anywhere that you made a mistake, the biggest probability is that you made the mistake by not remembering to transform the problem back, the results back to the original problem. You need to make sure if you do transform a problem into a new domain, if you will, so that it becomes simpler, easier to solve, you must translate your results back to meet the original problem, to be appropriate for the original problem. Okay, so now we've got these new equations, we've seen they are able to calculate the exact same results as our previous equations, but by translating the problem so it's easier to solve, solving it and then translating the results back, we have made our lives a lot easier. When we combine the line and circle equations together, they were a lot easier to expand because the equations were simpler. And then the calculation of the points of intersection is now more simple. There's less operations, which generally makes life easier. Now, as I mentioned at the beginning of the video, the most important thing that we've covered in this video is actually the fact that you can translate a problem, solve it, and translate the results back. Now, this is an incredibly important concept, and it's something that makes solving problems of any kind a lot easier. Yes, being able to intersect a line and a circle is useful, but understanding this overall concept that we've employed in this video is going to be of a lot more use to you than just knowing how to intersect a line with a circle. Now this is the final video on this DVD that covers analytic geometry, so I really hope that you did enjoy and benefit from the various topics that were covered on this DVD, and I hope you will join us in the other volumes in this series where we're going to continue to use mathematical theories to solve computer graphics and programming related problems. So if you have any questions or feedback, or perhaps you're working on your own mathematical problems and you need some assistance, be sure to head over to the forums at 3dbuzz.com, where you're going to find a community of knowledgeable and helpful members who are always happy to assist you. So thanks again for watching. I really do hope you enjoyed it, and I hope to see you again soon. Thanks a lot, everyone.